Hello everyone, welcome to the next episode of the Milky Way podcast where we talk about Big Bang to black holes and everything in between. For today's episode, we are going to talk about very interesting topic of planetary interiors. And to join the conversation, I have Professor Chhavi Jain with me. She's a planetary scientist and she explores the planetary interiors in our solar system. Welcome to the episode, Chhavi.
Hi, Tej. Thank you for inviting me here. It's a great honor to be part of this podcast and to be talking to your viewers as well as you about planetary interiors.
Thank you so much. And to start with, I want to ask you, what is planetary interior? Like when we say we are studying the planetary interiors, what are we actually studying?
Great. So that's a great start to our conversation today. So, in very simple terms, the planetary interior is anything of the planet that you don't see on the exterior, on the surface. So, this could be something that is below the surface of the planet.
I see.
Our planet is not, especially in the context of the Earth, on the outside we have the atmosphere and the gaseous layers. Then we have the surface which we see around us. This has rocks and it has oceans. But then we have this whole part of the planet that we don't see, which is also composed of rocks and metals that behave differently from how they behave on the surface. So while we study the interior, we study how the planet is behaving inside. And for the Earth, this is extremely important because though it may not seem like that in everyday life, the interior actually affects our surface to a very large extent, especially on the Earth. You may have heard that something called plate tectonics. Earth has plate tectonics, which means that our surface is divided into a number of plates that move around. And it is the interior processes that are controlling the movement of these plates. And this movement is ultimately shaping all the geology that you see around us. It is regulating the different water cycle, the carbon dioxide cycles and everything that we see around us. So in a way, the interior is actually helping us survive on the surface. So that is why it's very important to study the interior.
I see. So also studying the interior, it's very important as you said, but it's again the interior. We do not see these things. We do not have access to it. So how do you study the planetary interiors or Earth's interior?
Yeah. So again, talking in the context of the Earth, as we go deeper into the planet, the temperature and the pressure increase quite a lot. So while if you look at the very subsurface layers, say a few kilometers deep, you could potentially drill into them. And this is what people normally do as well. They create boreholes, or we have mining in which we're basically just digging up the surface. But then I think the deepest borehole on the Earth's surface is, I think, 12 kilometers deep, if I'm not wrong.
Oh, just 12 kilometers.
That's it, yeah.
Oh.
So beyond that, the temperature and pressure already become so high that our drilling machines cannot survive. So then the question, as you correctly asked, is how do we probe deeper inside that? So then what we use are called geophysical techniques mostly.
I see.
So we make use of certain properties of the interior processes that we see on the surface. For example, we do feel earthquakes. Earthquakes are something which are related to the vibrations of the earth, which we can physically measure on the surface. But then by understanding how these vibrations are created and how different materials vibrate, you can kind of you can go backwards and try to understand where these vibrations are coming from and what the properties of that layer of the earth would be that is producing these vibrations.
I see.
So seismology is one of the most important ways in which we probe the earth, at least. Then other techniques are, you could be studying how the gravity varies on the surface. So we usually just think of gravity as a constant, but the gravity does vary over the entire surface of the earth. Depending on, say, you might have a heavy metal deposit in the deep earth, somewhere in the deep crust. Locally, that would produce a gravity high in that region. So that is how, if you study the gravity variations, you can study what the composition of the interior and sometimes some kind of dynamic processes also affect gravity. So gravity measurement is another way in which you probe the interior. You could also be studying how the heat flux varies on the surface. Again, that is connected to your interior processes, because say if you were to study the heat, measure the heat flux above a volcano, it's going to be much higher than the heat flux that you say even measure right here. So that also tells you what kind of temperatures you have in the interior, how the temperature varies in the interior, and things like that. So these are some of the geophysical techniques that we use to study the interior of a planet.
I see. That's amazing. So, as we know, like our Earth, when it formed, when our solar system was forming, it was really hot, and the interior is again like really hot. So, how the heat is transferred from the inner regions of the Earth's interior to the outer regions?
That's a great question. And that is kind of where my research focuses on at the moment. So, as you rightly said, the Earth's interior is much hotter than its surface. So, just by physical laws of thermodynamics, heat must be going out from the interior to the exterior. Now, classically, for at least solid bodies, like the Earth, we would have two primary processes by which heat is transferred. One is conduction. Conduction involves just the transfer of heat by across two surfaces that are in contact with each other, and these are probably solid surfaces. But then for the Earth in particular, we know through different geophysical techniques that the core is molten, whereas the mantle is a solid rock. But over very long time scales, this solid rock actually behaves more like a fluid. So I can give you an example of say if you visit very old monuments that have glass windows. Over time you might see that those monuments would have glass windows which have kind of patchy glass on them.
Yeah, I remember.
Right?
Yes.
So that looks like glass has flown over time,
Yes.
even though it is a solid. So it's some materials have this property that over very long time scales, if the temperature is not too cold, they tend to flow like a fluid, even though they are solid in nature. So this property allows. So the same thing happens in the rocks inside the Earth, because the temperature is high enough, but it is not so high that the rock would melt. The rocks are hot but not molten. So in this case, they are able to flow like a fluid, and that is how they are able to take heat from the core to the surface via something called convection, in which our rocks are actually flowing like this circular motion. They're taking up heat from the core, transferring it to the surface, getting cooled down, and they sink back to the near the core, and this process continues. So this is called convection, and that is one of the main reasons, well, not the main, but it is an important reason why Earth has plate tectonics on the surface, because this whole circular motion of our rocks is aiding in the motion of the surface plates.
I see.
That are kind of riding on the circular motion of the rocks underneath.
So that's really interesting to know. So that brings me to two more questions.
Yes.
So first one that I wanted to ask is, so is this process same now also in Earth's interior as it was when Earth was much younger and much hotter, or it has changed, or it has stayed same?
So that's a very important question, but I think there is no easy way to answer it. It remains an active area of research. In fact, this is one of the outstanding questions in geophysics nowadays, because we don't, I think, okay, what I can say for sure is that when the Earth was just formed, it was extremely hot, possibly even molten. We had something called a magma ocean. So obviously when the rocks at that time are hot, they are liquid, they would be flowing, they would be moving much faster. So you would have convection at that time. Now, whether you had plate tectonics or not is what we don't know. So convection is a way, as I said, a way for our mantle to transfer heat from the core to the surface. Convection was possibly happening much faster in the past when the rocks were hotter, there was more heat in the core at that time, and the rocks were just hotter and molten. Then eventually the rocks cooled down, they became solid. But as I said, because of this property of our rocks that even hot rocks are able to behave like fluids over very long time scales, they still convect, but I would say convection has slowed down over time. But it is unclear at what point this convection also produced, well, not produced, but at what point this convection was aided by plate tectonics or not. I think that remains a highly debatable and an area of active research these days.
Oh, that's really amazing. So now, yeah, my second question is now
Yeah.
you have mentioned plate
Yeah.
tectonics couple of times. I myself and I guess the listeners are also curious to know what are
Yeah.
plate tectonics.
Yeah.
We keep hearing about like plate tectonics are causing
Yes.
so many important phenomena. So what are plate tectonics?
Yeah.
We want to know the basics.
Right. So, plate tectonics are a very unique feature of the Earth. As I said, well, on the surface, plates manifest in the form of actually the surface being broken up into pieces. So, you must be familiar with terms like the continental crust and the oceanic crust. So, the continental crust basically overlies the continental plate, and oceanic crust overlies the oceanic plate. So basically, so let's start with the interior of the structure of the interior of the Earth. We have the crust, which we see around us. It is the coldest part of our surface. Um, Below the crust is something we call the mantle. Here, the temperature and pressure is higher, so the rocks are hotter, but they may or may not be molten. But this increase in temperature allows the rocks to behave like fluids over very, very long time scales. On the crust, the rocks are too cold. They usually will not behave like fluids even over very long time scales. So the difference would be on the surface, if you keep a rock and say you put a hammer on it, it'll break, it'll be brittle. That is what I mean by it's very cold. But then, if you pick up a mantle rock inside the mantle, so under those conditions, if you strike it with a hammer, the rock may not break, it may deform like a plastic.
I see.
Right? So if you can imagine plasticine. If you put pressure on a plasticine roll, the plasticine ball will not break. It'll just become, it won't be spherical anymore. It'll just assume some other shape. So that is plastic deformation. So that's how your mantle rocks behave. And then below the mantle, in the very interior, is your core. This is a metallic body. So I am right now talking mostly of the crust and the mantle. As I mentioned before, the crust is very cold and it's brittle. Now the mantle, even though it is warmer than a crust, the upper few kilometers of the mantle are still not so hot that they would immediately deform plastically. So this part of the mantle which is still not hot enough, as well as the crust, together is called the lithosphere. This is the cold part of our planet, and this behaves in a brittle manner. So in this region, the rocks will break if you apply enough stress on them. So this is where the plates exist. For somehow the plates, this lithosphere of our planet has undergone stresses in such a way that it has broken up into pieces, and each piece is called a plate. And these plates on the Earth are not static, they keep on moving around.
I see.
And this is called plate tectonics.
Oh, amazing.
Yes.
So this is kind of floating thing. Can we say it in that way?
Yes. Yeah. So your mantle rocks are hot and they deform plastically. And on the top of them are your lithospheric rocks, which are brittle, they are cold, and they behave like solid bodies. So they're kind of floating over your hotter mantle.
I see. So yeah, that's like absolutely like blows my mind, like how the interior of our planet works. Like
Yes.
yeah, because by being in the field of astronomy and astrophysics, you are so used to looking outside the Earth, and sometimes you forget
Yeah.
how amazing phenomena are happening
Yes,
within our planet.
Exactly. Yeah, you're right. I think studying the interior of the Earth is almost like introspection.
True, true. So these plate tectonics are the reason for earthquakes, if I understand it.
Yes.
Okay. So how does
on
it
the
happen?
Earth,
Uh-huh.
in particular on the Earth, plate tectonics are very big contributors for earthquakes. So as I said, these tectonic plates are constantly moving, and they behave like these solid bodies that find it difficult to deform plastically. So as they move, they strike each other. That is, I mean, in general, they do strike or they move away from each other. Every time they strike with each other, the stresses build up in each of the two plates that are striking with each other. By striking, I don't necessarily mean a collision. They may be moving against each other too. But this motion and this collision, in a way, at least these stresses that build up during these motions build up inside the lithospheric plates that are very hard. So eventually, for some time, they are able to tolerate the stress, but at some point, the stress becomes too much for the plate, and then either the plate would crack or there would be some kind of release of stress. And this release manifests in the form of an earthquake, which is a vibration. So usually it's some kind of a crack which is forming that is then emanating into different waves that propagate throughout the earth.
Oh, I see.
Yeah.
And then we keep hearing like some places on our planet are
Yeah.
more prone to earthquakes.
Yes.
And some are not. So
Yes.
what
Yeah.
causes that part?
Yeah. So as you can imagine, the places that have more plate tectonic activity, or maybe perhaps faster plates, more rubbing of plates against each other, would be more prone to earthquakes, because those areas would be where more stresses would be accumulated over time. So usually areas that are on the boundary between two plates are more susceptible to earthquakes, because it is at the boundaries that your stresses are accumulating. And it is usually at the boundaries that the stresses are finally released, because the boundary is kind of a weak zone. The interior of the plate is very cold and it is very hard. It would be very difficult for a plate to break there and release stress. Whereas the boundary between two plates are already a weak zone, because that's where the plate has already cracked in the past. So that is why the boundary regions would be more prone to earthquakes. Also, I should have mentioned this earlier. When we talk of plate motion, we talk of three types of plate motions in particular. One is collision motion. Collision between two plates can either lead to one plate subducting underneath the other, or it could lead to both plates making a mountain. They're kind of uplifting. The other motion is divergent, where two plates are moving away from each other. And the third is transform boundary, where the plates move against each other. They neither collide nor do they move away from each other. So usually earthquakes are most common in subduction region, where two plates are colliding. So so again, you have more earthquakes being concentrated near plate boundaries, and that too more near the convergent plate boundaries, where you have collisions taking place.
I see. And is there any way that we can monitor these movements and predict the earthquakes beforehand, so that we can take all kind of precautions?
I know, I wish we did. I wish I had a better answer to this. People do monitor, of course. We have a huge array of seismometers over most of the surface of the earth, where people are monitoring plate motions, they're monitoring seismic activities. But I think we are a little far from actually being able to predict an earthquake beforehand. I think right now we can maybe predict an earthquake maybe a few seconds before, when we are able to detect heightened seismic activity. But earthquake mechanics are so complicated that the physics for it, we are still working on it. So many people, like seismology is one of the most popular fields of geophysics, and it is also one of the most abundant data sets, the seismic data set. But still, the mechanics of the whole process are so complicated that predicting an earthquake remains a matter of research right now. I don't think we are very good at it at the moment.
I see. I hope in future, as you said, like we
Yes.
have some advancements, and
Yeah.
because that's a really scary part, like as we have seen couple of times, like many times in the past.
Yeah.
So now we have talked a lot about the earth and earth's interior.
Yeah.
So now I want to move to the solar system, like other bodies in the
Yes.
solar system.
Yes.
So do we have not earthquakes? I always keep saying, do we have earthquakes on other planets? Not earthquakes, but do we have quakes on other planets as well?
Yes. So for a fact, we know that Moon and Mars have quakes. So I think people often just call them moonquakes and Marsquakes. I don't know if there are better words out there for them. But at least I think one of the Apollo missions had installed some seismometers on the moon surface. And recently, I think InSight, I could be wrong, but one of the more recent Mars missions had also installed seismometers on Mars. So we know for them that quakes do exist on these two planets.
I see.
For other planets, I think recent research has suggested that Mercury could also have quakes on its surface. But right now, we don't have any probes on its surface yet to be able to actually see whether it does or not. Similarly, other planets might too. We just don't know enough yet.
And the reason for quakes on other planets and satellites, is it the
yes.
tectonic activity, or do we have some other mechanism?
Yeah, so that is a very, very interesting question. As far as I understand at least, the quakes on Moon and Mars and even on Mercury don't happen for the same reason that they happen on Earth. So Earth is very unique in that it has plate tectonics. At least in the solar system, we haven't seen any other planetary body that has a plate tectonic activity on its surface. For Moon and Mars and Mercury, the most popular reasons for quakes on the surface is probably that these planetary bodies are contracting. Because they are very small in size, it is proposed that these planetary bodies have already lost much of their interior heat. So over time, they have cooled so much that the planet is actually now contracting because of its thermal cooling. And because of that contraction, the surface is actually becoming smaller and it's cracking because, as I said, the surface on almost all planets is brittle. So these brittle rocks on the surface are over time, because of cooling, crack, and that generates quakes. But because, at least as far as we know, these planets don't have plate tectonic activity, so it's not subduction, it is not any kind of plate motion that is causing the earthquakes, it is simply contraction, thermal cracking. That is causing these quakes.
That's really interesting.
I know, right?
So, and also so in a way, like our Earth is special. Huh?
Yes, yeah.
So, in a way, only our Earth has plate tectonics and Earth is habitable also.
Yes.
Is there any correlation between
Yeah.
these two things, or is it just a random guess from my
Yeah,
side?
I think now we are going into more unknown territories. As far as I know, initially that's what people thought, that Earth is the only planet with plate tectonics, at least today. Earth is the only planet that has habitable conditions today. So probably the two phenomena are linked. And certainly plate tectonics helps maintain life on Earth because, at least for us, it is maintaining the carbon dioxide cycle, it is maintaining the water cycle, it is maintaining the recycling of minerals from the interior to the surface and back in. So it is maintaining the habitable conditions on our planet at least. However, more recent studies have suggested that plate tectonics is probably not necessary, but it may be important to sustain conditions over very long time scales. However, it could be possible at least to have life on planets that don't have plate tectonics, but it is yet to be seen whether that life would be macroscopic life or like human life, or we are talking about microscopic life now. Just microscopic life could be possible even on planets that don't have plate tectonics, but I am not so sure about more macroscopic life.
I see.
But I think, again, this remains an area of active research.
I totally understand. Yeah, it's not that straightforward to figure it out.
Yes.
Also, I'm now thinking about the plate tectonics. Do we have any observations or any calculations which can determine like when this plate tectonic activity started, or when this particular layer was formed, or in
For
the
the
past, for the
Yes.
Earth, like how long back in the past?
Yeah.
did-
So people, again, I think the geophysics community is divided over this. Some people believe that some kind of plate tectonics, or sometimes they call it, I think, proto-plate tectonics, like some form of
I
plate
see.
tectonics occurred from the early Earth itself.
like the protoplanet
Well,
era?
protoplanet would be too early, but probably after the magma ocean solidified and we at least had a solid mantle and a solid crust. Many scientists believe that soon after the crust, the lithosphere basically broke into plates, and we started some kind of tectonic activity, even if it wasn't as full blown as we see today, but some aspect of it was there even at that time. But there is another community of people in the geophysics community that believes that no, plate tectonics is much more recent. And I think one of the reasons for that is, so Earth has, as I mentioned before, we have a continental plate and an oceanic plate. These are the two types of plates that we have on the surface. There are some differences between the two plates. One of the most important differences is in their composition. The oceanic plate is heavier and your continental plate is lighter and thicker. So that's why it's more buoyant. That is why you see continents being above the surface.
Okay.
And the oceanic plate is denser and it is thinner. So that's why the oceans are kind of more subdued than the continents. This is because of the difference in their composition. And the way a continental plate is formed is through the recycling of old continental plates. So to form a continental plate at all, you would think that you would require a continental plate in the
Yes.
past. So that is why some people believe, well, that's a very simplified reason. That's not the only reason, but that's one of the main reasons why people believe that we might have had plate tectonics from the very beginning, where you already had this recycling of crustal material, which you do not see on planets that don't have plate tectonics. Because those planets like Mars are just a single plate planet. There's no subduction, there's no recycling of plates like we see on the Earth. But then there are processes by which you can form the first continental crust too. And that is why there is another community of scientists that believe that, oh, maybe a long time ago we had those processes that first formed a continental plate. The formation of that plate didn't necessarily require plate tectonics to be taking place, but it is only after that continental plate was formed and you had the separation of continental and oceanic plates that plate tectonics started. But obviously, this whole question is much more complicated than how I'm explaining it right now. This is just one of the reasons that people are divided in their views. But again, I think this remains a topic of research. We really don't know when plate tectonics started.
It's a really, really complex topic, Leah.
Yes.
I'm
Yeah.
like so amazed to know all these things about the Earth's interior. Like, as I was earlier saying, we keep thinking about stars and the outside planet
Yeah.
Earth. Like, there is so much interesting going beneath the
Yes.
surface. So now we have talked about the planets in our solar system, our Earth. I wanted to move to the exoplanets area.
I
So,
see.
do we have any evidence of having tectonic activity or plate tectonics, or is it a really far-fetched idea to think about like observing
Yeah.
plate tectonics on those exoplanets?
No, I think that's a question that many people have asked. But as I mentioned before, this whole topic of plate tectonics, we don't even fully understand how plate tectonics started on Earth. Also, detecting plate tectonics is, of course, is an important part of the answer to your question, and that is also difficult to answer because plate tectonics is it's not a thing that you can observe; it's a process. So, in order to, the most obvious way in which you can say that a planet has or does not have plate tectonics is you keep observing its surface. If you see over time the surface is changing, things are moving around, you would say it has plate tectonics. But we don't even have that much data for the Earth, let alone another planet. So that is why it's very difficult to say whether a planet has plate tectonics or not. So the way we could perhaps not detect, but guess whether a planet has plate tectonics or not is looking at certain markers that we think are contributed only by plate tectonics and not by any other process.
I see.
So one of those are if you could measure the seismicity over the entire planet, and you find evidence like you find on the Earth that seismicity is localized in regions, in certain linear regions, and you don't see much seismicity elsewhere, then you could say that, oh, maybe those regions are plate boundaries. And the other regions that don't have a lot of seismicity, maybe those are plate interiors. But again, that is hard to do. We haven't even landed on most of the planets yet. And for exoplanets, we haven't even reached there. So for doing this for exoplanets is right now out of the question. But for even other planets, planets as close as Venus and Mars, also we don't have enough data. Second thing could be if you could again map all the gravity signatures throughout the planet, and you could maybe measure the topography of the planet. So if you see high mountains, you see low basins, may or may not be covered with oceans, but if you see topographic differences and you see gravity differences over the planet, there are ways to correlate the two and infer what is happening in the interior of that planet that could have produced that topography. And some of those processes could lead to plate tectonics. But again, there are many ways in which you could have mountains on a planet. It may not be a plate tectonic process at all. You could also have, like, for example, Venus. We don't know whether Venus has plates today or not, but it does have very high lands, at least, even if not mountains. So there are processes by which even planets without plates could produce mountains. So another signature could be heat signature. So if you could measure heat flux over the entire surface of an exoplanet, then again you could see localized regions where you would have high heat. Those regions could correspond to activities like volcanism, or they could be regions where there is heightened plate activity that is generating more heat. Also, like on the Earth, you have where plates diverge from each other. New molten rocks come to the surface and new crust is formed in that region. And that, because it's molten rocks that are coming to the surface, it is associated with very high heat flux. So if on another planet you see these localized linear regions where you have high heat flux, then again you could say, oh, maybe this is something like a plate boundary here. So all I want to say is that there is no one evidence for plate tectonics. You would probably need to collect these different geophysical evidence and then see if they all correlate and they can all be explained by this one phenomenon. For exoplanets, we certainly don't have that kind of data, but I know it might be hard to believe, but even for the Earth, it was very late. It was only in the 1960s that people accepted the theory of plate tectonics.
Wow.
Yes.
This recent?
That recently, yes.
Oh my God.
So it was only in 1912 that I think a scientist called Alfred Wegener, he proposed that continents drift, because he saw that part of the American coastline, South American coastline and African coastline kind of complement each other. They look like puzzle pieces.
Yes.
And then he also correlated the existence of similar fossils across different landforms that are not connected to each other anymore. And then there were also evidence coming from, there was evidence of past glaciers in regions that don't have glaciers anymore. So collecting all these evidence together, Wegener suggested that continents seem to be moving around. And he suggested that in the past there could have been one supercontinent called Pangaea, which is now actually a working theory at the moment. But he proposed this all the way back in 1912, and people didn't believe him, because he did not have a mechanism. He couldn't explain how the continents are moving. So it was only, I think, during the World War II then that countries like the US deployed a lot of studies of the ocean basin. And there they found the existence of high heat signatures and high seismicity along the boundaries that are divergent boundaries. So these divergent boundaries in plate tectonics occur at mid-ocean ridges. So when two oceanic plates move away from each other at divergent boundaries, as I said, you have molten rocks that are coming to the surface. And this region where the new crust is formed is called the mid-ocean ridge. So it's a ridge in the middle of the ocean, basically. So during the World War II, whatever data was collected in the survey of ocean basins, then people found out the existence of these mid-ocean ridges. Also, with time, they found that these ridges have symmetric signatures of magnetism on it. So these magnetic strips was in the sense that they found that along ocean ridges, you have parallel strips that have this on either side of the ridge. You have strips that have some magnetic strength of the rock, And then beside that is another parallel strip that has a different strength. And the polarity of these two adjacent strips are reverse. So over time, people concluded that, okay, maybe what was happening is Earth's magnetic field was flipping, and this was being recorded in whatever rock was getting solidified at that time in new crust. And this new crust was forming in the middle of the ocean. So when at say time t, some new crust formed, you had hot magma come up to the surface. It was influenced by the Earth's magnetic field. It incorporated this magnetic field in it, and over time, as the magma froze, the magnetic signature of the Earth at that time got frozen in the magma, in this frozen rock. Then over time, these plates kept moving away from each other. So this strip of some whatever magnetic signature was there moved away from this mid-ocean ridge on either side. Then new magma was formed. This new magma had the new magnetic field signature in it. So this is what scientists found eventually, that not only did you have ridges, you also had these reversal of magnetic strips that are symmetrically found away from the magnetic ocean, from the mid-ocean ridges. So all of these evidence together led to people believing that this motion is being caused by the motion of plates, which eventually people also connected with convection. So once people proposed convection, then they had an actual mechanism by which the plates could move. And that is when, as late as in 1960s, our theory of plate tectonics even on Earth was accepted. So if it took that long for us to see, to accept what we already see on the surface of Earth,
planet where we live,
you can imagine how difficult it must be to detect this on another planet, which we are barely even able to reach.
Yeah, like I'm not just like, I still cannot believe it. Like we were on moon in 1969 and
exactly
still exploring such a huge part of the planet where we live.
Yes.
So, that's really, really surprising.
Yeah.
So, and for the next question, I wanted to ask you, like, what are the hot topics in planetary sciences? But I guess we have the answer already.
Exactly. We do have the answer. The hot topics, at least in this particular field, is that first of all, understanding how Earth has plate tectonics and no other planet has it. Many people today believe that an important factor in this is the fact that Earth has water on its surface, whereas many other planets don't. That could contribute to the rocks on the Earth becoming softer because of the presence of water. At least on Venus, that could be a case, that Venus' surface is so hot that it's whatever water it might have had on its surface has evaporated. And that could be one reason why Venus doesn't have plate tectonics today, as far as we understand at least. Same for Mars. We don't see signatures of water on Mars anymore. So that is why water remains a very strong candidate of why Earth has plate tectonics and others don't. But again, this is, I think, one of the most important questions that we need to answer. And second is, how did this plate tectonics, how did it evolve? When did it start? Will it end? When will it end? If maybe planets like Mars maybe one day had plate tectonics, today they don't. Is Earth also going to become like that one day? So these are some of the things people are trying to answer. And then of course, always trying to find out what are the signatures of plate tectonics. Can we use these signatures to detect plate tectonics on other planets?
I see. That's like, everything is super interesting, and
yes.
I'm sure like you enjoy working in this field.
Yes, absolutely.
And this is what I wanted to ask you the next, like how you got into this field, like when you were growing up, for you like interested in the field of planetary science in the starting, or you got into it over time?
Yeah, so I wish I had a more interesting answer to that. My background, I started with doing a BSc in physics. And by the end of my bachelor's degree, I was getting a little bored of just theoretical physics, and I wanted to branch out into a more applied field of physics. And that's when I heard about geophysics, and then I did my master's in geophysics. Now, in India at that time, geophysics was mostly concerned with understanding the physics of extracting oil. So this is about 10 to 12 years ago. At that time, most of the geophysics programs in India, and there weren't that many to begin with, most of them were focused mostly on exploration geophysics or oil industry. But we had one course on the interior of the earth at that time. And I think one of the main things we studied in that was the magnetism of the earth. And at that time, that really fascinated me. So I wanted to, from that moment on, wanted to do a PhD and wanted to do something to do with geomagnetism. So when I applied for a PhD program in the States, I specifically mentioned that I wanted to study geomagnetism. However, geomagnetism is not a very popular field of research. So one of the professors, my PhD advisor, answered saying that he doesn't exactly work on geomagnetism, but he works on mantle convection on the earth, which is very closely tied to geomagnetism, because convection in the mantle is essentially transferring heat from the core, and it is this transfer of heat from the core that is leading to core convection, that is leading to geomagnetism. So he said that in a way, if I want, I could later connect mantle convection to core convection. But he suggested that I maybe start with mantle convection. So that's how I got into the study of Earth's interior, at least. And then once I started doing Earth's interior, I vaguely heard about other planets. So in my postdoc, I wanted to branch out into planetary sciences. So whatever I had learned about rock deformation and plate tectonics on Earth, I tried to apply to other planets during my postdoc. So I think by training, I am a geophysicist, but I am now through experience becoming a planetary scientist.
Amazing. That's super interesting. And do you have any message for the young listeners who have listened to this podcast, and I'm sure they would be like really fascinated and they wanted to get into this field? Do you have any message for them?
Well, I think I would like to say something that has held great importance, at least in my journey, is the importance of uncertainties. So my whole PhD was about quantifying the uncertainties in our understanding of how rocks deform. And usually uncertainties are looked down upon because they're something that we are scared of. That, what we are certain of, we like. What we are not certain of scares us because we're not able to explain it. But something that my postdoc advisor told me, and I think that has become a mantra for me now, is you should not be scared of uncertainties, because if you have large uncertainties, then they give you a lot of opportunities to make new stories out of them. Because every uncertainty is like a different thread into which you could divert your story. So I think that would be my message to all the listeners, that don't be scared of any kind of uncertainties, be it in science, be it in life. Just take it as a challenge and just continue with your journey.
Amazing. That's like whatever you have said, everything. It's going to be super important for all the listeners.
Thank you so much.
And thank you so much for joining us for this episode and for all the insightful conversations. It was amazing. Thank you so much for it.
I had a lot of fun too, and I hope our audience were able to get something interesting out of this conversation.
Definitely.
Thank you.
Thanks to our listeners, and we'll see you in the next episode.
Thank you.